Euler's method for numerical integration. Euler's method is a numerical technique used to approximate solutions to first-order differential equations of the form dy dx is equal to f of xy. Note that doesn't mean necessarily that we have of the form f of x g of y. In other words, we're not guaranteed to have a separable differential equation here. So we may have an equations of type that we don't know how to solve from this course, or even one that can't be solved at all. So let's carry on and have a look at the method. It works by taking small steps along the tangent to the solution curve, using the slope given by the differential equation. It's related to tangent fields, and we'll have a look at that as we go along. The steps of Euler's method are: we start at an initial point, which we usually denote x0, y0. We calculate the slope f dash x0, y0, which means we're evaluating dy dx at that initial point to get the gradient there. So that's at the current point, which in the first instance is x0, y0. Use this slope to predict the next point. x1 is x0 plus h. H is the step length here. We've got a diagram coming up which will explain this a bit more. And then y1 is y0 plus h, which is the step length, times the gradient at the previous point. So h is the step size. We'll have a look at that in a moment. Then we're going to repeat this process to extend the solution over the desired interval. In general, xn plus 1, that's the next value of x, is the current value of x plus h. Yn plus 1 is the current value of y plus h, the step length, times the gradient at the current point xn, yn. Alternatively, we can write this as, and I find it a bit easier to understand this way, the change in y1 is equal to dy dx evaluated at x0, y0 times the step length, and then we get that x1 is x0 plus h, and y1 is y0 plus delta y1, the change in y. In general, we have delta y n plus 1 is dy dx at xn yn, so the next change in y is equal to the gradient at the current values of x and y multiplied by the step length. Then we get that xn plus 1 is xn plus h, and yn plus 1 is yn plus delta yn plus 1. This diagram might explain that better if it was difficult to understand just from the maths. So we're assuming that we're at the start here. Our first point is x0, y0. And what we do is we calculate the gradient at that point. Now you can view this line here as being part of the tangent field calculated at this point. What we do with Euler's method is we then go a distance h across using the line here to approximate the curve. We're then calculating delta y1, adding that onto y0 to get y1. And so we arrive at our next point, P1, which is x1, y1. We then do the same thing again. We calculate the gradient there. So you can view that as being the tangent field at that point. And then we go this distance, another h, along in that direction. x1 plus h gives us x2. If we then add the y1 and the delta y2, we get the y2. So that's how the method works. And you might think to yourself, well, this is actually a curve. And what I'm doing is I'm going a straight line there, calculating the gradient again and doing a straight line there, calculating the gradient again, doing a straight line there. Doesn't the solution using this wander away from the curve? And the answer is yes, it does. But in practice, when people do this, they use very, very small steps, and therefore it doesn't wander that far away.